Next, we're going to introduce a common continuous random variable called the exponential random variable. And let's discuss where this fits into the context of some random variables we've learned so far. From our previous videos, we covered these 3 discrete random variables. There are 2 other discrete random variables out of the scope of this class, but they do, in some sense, capture, quote, time in the context really of the number of trials until one success or several successes. These are out of the scope, the geometric and the negative binomial. But what is in the scope is the exponential. This is actually a continuous random variable because it is going to be modeling the amount of time before the first success. And in particular, we're going to see in a minute how it is very related to the Poisson distribution. Okay, so what do I mean? Well, so let's assume you have some experiment. It's going to last some duration of time until a success occurs. Just like with Poisson random variables, we're going to assume that successes are independent of one another in terms of when they occur. They're independent of one another, and that they occur at some constant average rate. That's going to be related to the parameter lambda, which we'll see in the next slide. But for now, let's just look at the probability density function. This is only defined for x values greater than or equal to 0. And you can see here is one example for one given lambda of what this probability density function looks like here. And you can see that I have a higher probability density for smaller values of x, and then that probability density decreases as x increases. And that will always be the case, regardless of your parameter lambda. Lambda here is positive always, and we'll see why in just a minute. All right, so good examples of things like this, where the occurrence, like the time in between events, the occurrence of events are independent of one another, and they occur at some constant average rate, is like time until the next earthquake, or time for a request to reach a web server, or time for something to break on a given street. So let's address this lambda. What are the units of lambda just based on what we know about expected value? And let's go back to point this out. You can derive the expected value, which I do in the appendix. I'd recommend you try it on your own and then you can check. And then same idea, try deriving the variance. But we'll see that the expected value here is 1 over lambda. So using that info alone, what are the units of lambda? Go ahead and put this on pause. Okay, well, we know that the units of the expected value are going to be the same as the units of the random variable itself. So the expected value is time, which means if I solve for lambda, lambda has to be in units. Lambda units has to be units of 1 over time. Okay, but when have we seen this lambda with these same units? Well, yes, we saw this before in the Poisson distribution, and these are very related. So in particular, if your number of events per unit time follows a Poisson distribution, which means the time that each success occurs is independent, and the average number of, in this case, we have requests, but it should say successes over time is constant, then the time between events will follow an exponential distribution. So then you think, okay, wait, does that mean these lambda parameters are the same? And the answer is yes. In both of these distributions, lambda is that constant value that's your number of successes per unit of time. And that is also why lambda is always going to be greater than or equal to 0. All right, so let's actually calculate the cumulative distribution function for the exponential, because it's going to make our life a lot easier when we're calculating probabilities. So go ahead and continue this integral using just a little fun fact, a reminder of how you integrate e to a constant times x. All right, so finishing the rest of this integration process, I am now going to get 1 minus e to the negative lambda x. That is my probability, or my cumulative distribution function. Let's visualize this, remind ourselves what this means. Okay, so let's look at this first left side as an example. Suppose I want the probability x is less than or equal to 2. There's two ways I can calculate this. I can use the probability density function and calculate this integral, which will give me the area to the left of 2 underneath the curve, which is 0.86. Or I can use the cumulative distribution function, which has already done the integration for me, and I can just go to the value of 2 here and see what is the area underneath the curve. That's just going to be the value of this function, capital F, at 2. So I get the same answer. It's just faster because I don't have to do the integration. Okay, but what if I want a probability that x is greater than something? My cumulative distribution function only gives me areas to the left underneath my PDF. And so if I want an area to the right, I can just use the fact that the total area has to add up to 1. So I can do this area to the right is 1 minus the area to the left. And that's exactly what we're showing here. So if I do 1, showing you the 1 here, and then minus, I'm taking that difference right there, I'm getting 0.14. Okay, so let's try this. Suppose I tell you x is the number of hours of use until your laptop dies, which is a random variable. Let's model it as an exponential. Let's say on average, laptops die after 5,000 hours of use. And let's say you use your laptop 5 hours a day. What's the probability your laptop lasts 4 years? And I'm just going to put a little caveat here that if I'm saying it lasts 4 years, then I also want to account that it lasts 5 or 6 or 7. So really I want what's the probability your laptop lasts at least 4 years. Go ahead, put it on pause and see what you get. Okay, so x is the number of hours until the laptop dies. And then x, therefore, can be modeled, it tells me, as an exponential. But now I need to think of what's lambda. So lambda is the number of successes, or in this case, laptop deaths, per unit of time. My unit of time is in hours. So I see I have one death, one laptop dies every 5,000 hours. So I'm going to write my lambda as this. That's assuming that x is measured in hours. Okay, now I want the probability that the number of hours, okay, x, it's a probability that my laptop lasts at least 4 years. Now we need to translate 4 years into hours, assuming I'm using my laptop 5 hours a day. So let's take 1 day as 5 hours times 365 days in a year, and then times 4 years. And that will give me the number of hours that I would need my laptop to last, so I know that it lasts at least 4 years. All right, so that's actually what I want, and when I go do that, that's really saying the probability x is greater than 7,300. I can do 1 minus the CDF of 7,300, and that gets me a probability of right around 23%. Now, you may have thought, well, wait, what if I didn't want to use the CDF? You definitely could do this integral yourself. You could take the 7,300, integrate, and then integrate our actual exponential function. But it's not necessary to do all that extra integration because we did that once and for all when we got our CDF. So these will be the same, just pointing that out, but unnecessary extra work. All right, let's try another example. So based on historical data, major earthquakes, which we're going to define as ones with a magnitude of at least an 8.0, occur once every 500 years in California. What's the probability of 0 major earthquakes in California next year? Okay, now there's multiple ways I can think about this. And so here's what I want you to think about first. Let's think about how many years per earthquake and how many earthquakes per year. Think of what that ratio would be. And then choose which strategies, maybe more than one would work here, to try to answer this question. So take a minute, fill in the blue boxes here, and pick possible strategies. All right, let's try the blue box first. So years per earthquake. I have 500 years for every one earthquake, which means one earthquake. So 1 over 500 earthquakes per year is another way to think of that. I have two possible ways I can do this. So the first one is I can think of a random variable that's time until the next earthquake, right? And so then I could then model what's the probability that time is greater than 1 year. That would be 0 major earthquakes this year. The other way I could think of this is I could think of my duration as being 1 year long, and I could think of the number of events in a given duration of time, assuming that these events are independent and occur at a constant average rate, and that would be well modeled by a Poisson distribution. So I actually can do either here, and let's try both. Let's do it from the Poisson standpoint first. All right, so here I'm going to let x be the number of earthquakes just next year. And so lambda then needs to be the average number of successes per unit time, and we can see my unit time here is going to be years. So we showed on the previous that that's going to be the same as 1 over 500, so that's what I have here. I want the probability that x is equal to 0. And to do that, I can just use the probability mass function directly, because this is a discrete random variable. So probability x is 0 is going to be exactly equal to e to the negative lambda, which ends up being about 99.8%. Pretty good odds in our favor that there's not going to be a major earthquake. All right, let's see how we can get this exact same probability, though, by framing this question in terms of a different random variable, an exponential. So now I won't be using the number of earthquakes per given time. Instead, x is now going to measure time until my first event or my first success. Again, success is dependent on the eye of the beholder, so don't be too caught up in that meaning a positive thing. We're just meaning the first event. Again, lambda is the same, and so now I want the probability x is greater than 1. Okay, so I can use 1 minus the cumulative distribution function evaluated at 1, which is going to also get me back to the exact same value. So either way I frame this, I end up with the same probability, which is 99.8%. So this is a great example of showing how, because these two distributions are really related, that you can oftentimes choose how you want to set up the problem, and you'll still calculate, you'll get the same probability as your final answer, but it's just framing your random variable in terms of time instead of number of events. Let's look at how we can calculate exponential probability questions in Python. So we're revisiting this continuous distribution notebook. And if you come over here, we're going to pop down to the exponential distribution with Python. Okay, so one thing to notice is we've been using lambda. That's how this is defined in terms of the probability density function. But SciPy uses a variant that the input called scale is actually 1 over lambda. So just be aware when we go to put in things for the PDF and the CDF down here, instead of putting the x in lambda, you're going to put 1 over lambda for this parameter. And let's see, let's do this example where I'm saying x is the amount of time a postal clerk spends with a customer. The time is known from historical data to have an average amount of time equal to 4 minutes. With a parameter, lambda is 0.25. What is the probability that a clerk spends 4 to 5 minutes with a randomly selected customer? All right, so again, just to point out where that lambda is coming from, we have historical data has an average amount of time equaling 4 minutes. So number of events would be like visits from a customer per unit time would be 1 customer per 4 minutes. So that's why lambda is 0.25 here. All right, now I want the probability the clerk spends 4 to 5 minutes. So I have an exponential distribution, which we're going to plot down below, but let me just eyeball and suppose I'm doing something like this, and I want the area now between 4 and 5. So to do this, I'm going to take the difference between two CDF values. All right, so we're going to do, first think of this curve. I want to get the area underneath the curve to the left of 5, and then subtract off the area underneath the curve to the left of 4. So that's going to be doing stats.exponend.cdf, starting at 5, and then I do need to write scale equals. If you don't put scale in here, it won't know that that's what you're putting in, or it won't correctly have the right lambda. So scale equals 4, and then minus stats.exponend.cdf for scale equals 4. And I do that and I get probability roughly 8%. Let's plot it. So to plot it, I'm actually going to need to use the PDF function because that's giving me this actual graph here. And so I'm just picking x values between 0 and 10. This is just breaking up 0 and 10 so that I have 1,000 different points in there. So it just looks like a continuous line. And now I'm going to do stats.exponential.pdf of x, and then scale equals 4. And when I do this, that is the area that I'm calculating, and we got that area is approximately 0.08. So this is just an example of how you can implement this both visually as well as computationally in Python.